August 7th, 1942, 16:00 US Marines are wading through chest, deep surf onto a place most of them can't even pronounce, Guadalcanal. It's a steaming chunk of jungle in the Solomon Islands, and these men have one job that sounds simple on paper. Capture an airfield the Japanese are building. They take it in about 36 hours with surprisingly light resistance. The Japanese retreat into the jungle. Mission accomplished. Right, wrong, that's when the real nightmare begins. The airfield they've captured isn't finished. It's barely more than a cleared stretch of dirt, and this isn't just any dirt. This is tropical soil that's been baking under equatorial sun one moment and getting hammered by monsoon rains the next. When it's dry, it's hard as concrete. When it rains, it transforms into something with the consistency of chocolate pudding. The Marines look at this strip and realize they're standing on a problem that could kill them all. Because here's the thing nobody tells you about island warfare in the Pacific. You don't win by holding ground, you win by controlling the air above it, and you can't control the air without a working runway. The Japanese know exactly what they've lost. Within days, their bombers are pounding Henderson Field. That's what the Marines named it after a pilot killed at Midway. But the real enemy isn't the bombs. It's the mud. After every rainstorm, the runway becomes unusable. Wildcats and Dauntless dive bombers, the only air cover these Marines have, start sinking into the ground. Mechanics watch in horror as landing gear struts disappear into muck. One pilot tries to take off for an intercept mission, and his wheels dig trenches 4 feet deep before his plane even moves forward. He doesn't make it airborne. The Japanese bombers he was supposed to stop arrive unmolested 20 minutes later. Engineers try everything they know. They pack the runway with crushed coral from the beach. It washes away in the next downpour. They lay down pierced steel planking borrowed from bridge, building supplies. It warps and buckles under the tropical heat. They attempt compacting the soil with rollers. The rollers themselves get stuck. By mid-August, Henderson Field is operational maybe 3 days out of 7. On the bad days, the Marines on the ground are completely exposed. No air cover means Japanese ships can shell them at will. No air cover means enemy troops can be reinforced under the cover of darkness. The math is brutal and simple. Without a runway that works in all weather, Guadalcanal falls. If Guadalcanal falls, the entire Pacific offensive stalls for another year, maybe longer. Back in Washington, this problem lands on the desk of the Army Corps of Engineers. They're getting desperate radio messages from the Pacific that all say the same thing. We need a solution, and we need it yesterday. The Corps of Engineers isn't starting from scratch. They've been wrestling with the soft ground runway problem since before Pearl Harbor, running tests at airfields from Louisiana swamps to Alaskan tundra. But everything they've tried has failed in one way or another. And now they're watching those failures play out in real time 7,000 miles away in the Pacific. The first serious attempt came in early 1941, when engineers tested something called square mesh track. A grid of welded steel bars that looked like reinforced chain. Link fence made from rebar. The theory was sound. Create a rigid framework that distributes weight across a wider surface area. They laid it down at Langley Field in Virginia, rolled a B-17 across it, and watched the mesh fold like tinfoil under 30 tons of bomber. The steel wasn't thick enough to handle the concentrated pressure of landing gear, but making it thicker meant making it so heavy that you'd need a cargo ship just to transport enough mesh for a single runway. Then came the Hessian mat experiments in the spring of 1941. British engineers had reported some success using burlap fabric coated in asphalt as temporary roadway material in North Africa. American engineers figured if it worked for trucks, why not aircraft? They soaked thousands of yards of heavy jute fabric in hot asphalt, laid it across soft ground at Wright Field in Ohio, and ran landing tests with P-40 fighters. The first landing went fine. The second landing created ruts. By the 10th landing, the fabric had torn completely apart, and chunks of asphalt, soaked burlap, were jamming up landing gear mechanisms. The whole concept went into the rejection pile by June. The coral and gravel approach seemed more promising initially because it mimicked natural hardpan surfaces. In July 1941, engineers constructed test runways using crushed coral aggregate mixed with volcanic rock, materials readily available on Pacific Islands. They compacted it with steamrollers until it reached concrete, like hardness. For 3 weeks, it held up perfectly under continuous aircraft operations. Then came the rain, not a sprinkle, a proper tropical deluge that dumped 6 inches in 2 hours. The entire surface transformed into a slurry. Engineers watched as the carefully graded runway developed gullies deep enough to hide a man. Worse, once coral gets wet and breaks down, it's almost impossible to recompact. You essentially have to start over. Pierced steel planking Persby came closer to working than anything else. Developed by the British for rapid road construction, these were flat steel plates about 10 feet long and 15 inches wide with holes punched through them to reduce weight and improve traction. The US military started testing PSB for runways in August 1941 at Bolin Field. Engineers loved the speed of installation. You could essentially shingle a runway in days instead of weeks. But PSB had a fatal flaw in tropical heat. Steel expands when it gets hot, and under the equatorial sun, those plates would buckle and warp, creating ridges that could shear off landing gear. Pilots reported that landing on warped PSB felt like touching down on a washboard at 80 miles per hour. By autumn 1941, the engineering teams were running out of ideas and running out of time. December 1941 changes everything. Pearl Harbor isn't just a military disaster. It's a wake-up call that the Pacific Theater will demand solutions nobody has invented yet. The Corps of Engineers puts out an urgent contract request to American steel manufacturers. We need a runway surface that can be installed in days, support aircraft up to 50,000 pounds, work in mud and coral equally well, and survive tropical conditions without warping. Oh, and it needs to be light enough to ship across an ocean on cargo vessels already overloaded with tanks and ammunition. Carnegie Illinois Steel Corporation in Pittsburgh takes the contract. Their lead engineer, James Marston, looks at all the previous failures and realizes everyone has been thinking about this wrong. They've been trying to create a surface that mimics concrete or compacted earth. Marston's insight is simpler. Don't fight the mud, float on top of it. He starts sketching a design that looks less like a road surface and more like a flexible metal carpet. By February 1942, Marston's team has a prototype ready. It's a steel plank measuring exactly 10 feet long and 15 inches wide, but everything else about it is revolutionary. First, the thickness, 3/16 of an inch of high-strength steel. That's thick enough to resist buckling under load, but thin enough that each plank weighs only 66 pounds, light enough that 2 men can wrestle it into position without machinery. The engineers punch rows of holes through the entire surface, creating a pattern that looks almost like an industrial cheese grater. These aren't decorative. Each hole serves 3 purposes, reduces weight by roughly 30%, allows water to drain through instead of pooling on top, and creates edges that give aircraft tires something to grip. But the real genius is in the edges. Both long sides of each plank have interlocking features that Marston's team spent months perfecting. One edge has a raised lip with a hooked end that curves upward. The opposite edge has a corresponding channel. When you lay 2 planks side by side, that hook slides into the channel and locks, not with bolts or welds, just mechanical pressure. The connection is strong enough that a 50,000 aircraft can roll across the seam without the planks separating, but it's also flexible enough that the entire mat can bend and conform to uneven ground without breaking apart. The short ends of each plank have a different interlocking system, a simple overlapping joint where one plank's end slides under the next. This creates a continuous surface running the length of a runway without any gaps wide enough to catch a wheel. The overlap also means that as weight presses down, the planks actually lock tighter together rather than spreading apart. In March 1942, the Army runs tests at Camp Claiborne in Louisiana, deliberately chosen because the soil there is notoriously soft, almost as bad as Pacific mud. Engineers lay down 200 square feet of Marston's interlocking planks directly on top of unprepared swampy ground. They roll a fully loaded B-17 across it. The mat flexes. You can actually see it ripple as the weight passes over, but it holds. They run 50 takeoffs and landings over 3 days. The mat develops some surface scratches, but 0 structural failures. When they pull up a section to inspect underneath, the ground has compressed about 2 inches, but the interlocking system has distributed that compression evenly. There are no stress fractures, no separation at the seams. The military orders 60 million square feet immediately. Understanding why these mats worked requires looking at the physics of what happens when a 30-ton bomber lands on soft ground. The problem isn't the total weight. It's how that weight gets concentrated. A B-25 Mitchell bomber weighs around 35.0 pounds fully loaded, but all that weight presses down through 2 main landing gear struts and 1 tail wheel. Each main gear has 2 tires, which means you're concentrating 35.0 pounds onto roughly 4 square feet of contact area. That's nearly 9.0 pounds per square foot, hitting the ground every time a plane lands. Soft soil can typically support maybe 300 pounds per square foot before it starts giving way. You don't need complex math to see the problem. Marston Mats solves this through load distribution across multiple planes, literally multiple planks working as a unified system. When a landing gear wheel touches down on one plank, that plank doesn't act alone. The interlocking hooks and channels mean the force transmits immediately to the 4 adjacent planks, 2 on each side and 1 in front and behind. Those planks in turn share the load with their neighbors. It's a cascading effect. By the time that 9.0 pounds per square foot reaches the actual ground underneath, it's been spread across roughly 100 square feet of mat surface. The ground now only sees about 90 pounds per square foot, well within the bearing capacity of even terrible soil. The flexibility of the system is just as critical as its strength. Concrete runways are rigid, which works beautifully on solid foundations but fails catastrophically on soft ground. When one section of concrete sinks even slightly lower than the surrounding area, the rigid slab cracks. Once it cracks, water infiltrates and the whole thing deteriorates rapidly. Marston Mat doesn't crack because it isn't trying to be rigid. Each plank can move independently by tiny amounts, we're talking fractions of an inch, while still maintaining that interlocking connection. The entire runway surface essentially floats on the ground like a giant steel raft, conforming to whatever settling or shifting happens underneath without breaking apart. The holes punched through each plank do more than just reduce weight. They create what engineers call a semi-permeable surface. When it rains, and in the Pacific it rains constantly, water doesn't pool on top of the runway, creating hydroplaning hazards. It drains straight through the holes. But here's the clever part. The holes are only about 2 inches in diameter, which means aircraft tires, which are much wider, still have plenty of solid steel to grip. The tire sees an effectively solid surface while water sees a drain. Testing at Airfield in April 1942 showed that water cleared from a Marston Mat runway 6 times faster than from solid surfaces. The interlocking edges also solve a problem nobody expected: bomb damage repair. When a Japanese bomber puts a crater in your runway, you can't just patch Marston Mat like you'd patch concrete. You have to replace entire sections. But because the planks interlock without welding or bolting, repair crews can simply unlock the damaged planks, slide them out and drop new ones into place. At Henderson Field, engineers timed this process. A bomb crater that destroyed a 20-foot section of runway could be fully repaired and operational again in under 40 minutes. That's not including filling the crater itself, just replacing the mat surface. Compare that to concrete, where a similar repair might take days and require specialized equipment to pour and cure new material. The system's simplicity meant training requirements were minimal. You didn't need specialized engineers to install Marston Mat, just men who could follow a pattern and work fast. Henderson Field, August 17, 1942. The first shipment of Marston Mat arrives on Guadalcanal aboard cargo ships that had to run a gauntlet of Japanese submarines to get there. Naval Construction Battalion personnel, the CB, unload 36 tons of steel planking onto the beach, while Zero fighters strafe the shoreline. They're working against a deadline that isn't measured in days. It's measured in hours before the next Japanese bombing raid. The CB have never seen this material before. Most of them were civilian construction workers, a few months ago carpenters, steel workers, equipment operators pulled from jobs building highways and bridges across America. Now they're in a combat zone, trying to figure out how to assemble a runway from scratch, while people are actively shooting at them. The first thing they realize is that 66 pounds per plank sounds manageable until you're carrying those planks hundreds of yards in 100-degree heat with 90% humidity. They develop a rhythm out of necessity. Two-man teams grab planks from the stockpiles and haul them to the runway edge. A third man acts as guide, positioning each plank so the interlocking edges line up properly. The first row goes down relatively easy. They're just laying planks side by side on cleared ground, but every subsequent row requires that hook and channel connection. The technique they figure out: tilt the new plank at a slight angle, slide the hook under the channel of the already placed plank, then drop it flat. When it seats properly, you hear a metallic click that becomes the most satisfying sound these men know. That click means it's locked. The work happens in frantic bursts between air raids. Japanese bombers are hitting Henderson Field almost daily, sometimes twice a day. The CB learn to watch for spotters. A single reconnaissance plane means bombers are maybe an hour behind. When the call goes out, everyone drops their tools and runs for foxholes. The bombers come over, drop their loads and leave. The CB wait 10 minutes for unexploded ordnance to cook off. Then they're back on the runway, continuing where they stopped. If a bomb hits the section they've already completed, they unlock the damaged planks and replace them. If it hits the section they haven't reached yet, they fill the crater with coral and keep laying mat right over it. August 20th, 3 days after the first mat arrives, a section of runway 200 feet long and 75 feet wide is operational. It's not a full runway. Henderson Field will eventually need 5,000 feet to handle bombers safely, but it's enough for fighters. That afternoon, 19 Wildcat fighters and 12 Dauntless dive bombers fly in from the carrier Enterprise. These aircraft, designated VMF 223 and VMSB 232, become the famed Cactus Air Force, named after Guadalcanal's radio call sign. They're landing on a surface that didn't exist 2 hours earlier. The pilots report that landing on Marston Mat feels different from concrete or compacted earth. There's a slight give to it, a flex you can feel through the landing gear. Some describe it as landing on a firm trampoline. That flexibility actually makes it more forgiving. Planes coming in too hard don't bounce as violently because the mat absorbs some of the impact energy. By September 5, 1942, Henderson Field has a complete Marston Mat runway 5, 200 feet long and 150 feet wide. Total installation time, including delays from air raids and artillery fire, 19 days. Traditional concrete construction would have required at least 3 months under ideal conditions, which nothing about Guadalcanal qualified as. Guadalcanal proves the concept, but it's what happens next that shows the true strategic value of portable runways. By early 1943, the US military is planning an island-hopping campaign across the Pacific that will eventually cover 7 miles from the Solomons to the Japanese home islands. Every single one of those islands will need an operational airfield, and they'll need it fast. The Japanese strategy depends on turning each island into a fortress that takes months to capture. Marston Mat collapses that timeline. February 1943, Russell Islands. The Marines land expecting heavy resistance, but find the Japanese have evacuated. Within 60 hours of the first troops hitting the beach, CB have a fully operational fighter strip, laid with Marston Mat. The speed is so shocking that when Admiral William Halsey flies in to inspect it, he asks the battalion commander if they started building before the island was actually secured. They hadn't, they just gotten that efficient. The Russell Islands Airfield immediately provides air cover for the next leap up the Solomon's chain, cutting what would have been weeks of vulnerability down to days. Munda Point on New Georgia Island, August 1943. This one's different because the Japanese are still there, dug into bunkers overlooking the airfield site. The CB lay Marston Mat while under direct fire. They develop tactics that sound suicidal but somehow work. Half the battalion lays planks while the other half provides covering fire with rifles and machine guns. Casualties are significant, 14 men killed, 7 wounded, but the runway is operational in 11 days. Marine Corsair fighters start flying missions from Munda while Japanese snipers are still being cleared from the perimeter. November 1943, Bougainville. This is where the military starts experimenting with prefabrication. Instead of laying individual planks, engineers back in Australia start pre-assembling sections of Marston Mat into panels measuring 50 feet by 15 feet. These giant sections get loaded onto LSTS landing ship tanks and transported intact. When the LSD beach at Bougainville, cranes lift these pre-assembled sections directly onto prepared ground. A runway that would have taken 2 weeks to install plank by plank goes down in 4 days. By December, Bougainville has 3 complete Marston Mat runways, forming a triangle pattern that allows simultaneous takeoffs and landings regardless of wind direction. The Marston Mat production numbers tell the story of how central this technology became. In 1942, Carnegie, Illinois, and 9 other steel manufacturers produced 8 million square feet. In 1943, production hits 40 million square feet. By 1944, it's 60 million square feet annually, enough to build a runway from New York to Philadelphia if you laid it end to end. The military is using so much Marston Mat that it creates a steel shortage for other programs. Tank production gets temporarily reduced because the furnaces are prioritized for runway matting. January 1945, Lingayen Gulf in the Philippines. This operation uses Marston Mat in a way nobody originally intended. Engineers lay it across sandy beaches to create instant piers and roadways for supply trucks. They discover the mat works just as well for distributing wheeled vehicle loads as it does for aircraft. Supply convoys that would normally bog down in beach sand can now drive directly from landing craft to supply dumps inland. February 1945, Iwo Jima. This might be the most famous Marston Mat installation of the war, though few people recognize it. The volcanic ash on Iwo Jima is so fine and loose that it's like trying to build on powdered sugar. Concrete won't cure properly because the ash gets mixed into it. Compacted earth is impossible because there is no earth, just ash. Marston Mat becomes the only viable option. CB lay it across all 3 airfields on the island, while the battle for Mount Suribachi is still raging. The war ends in August 1945, and military planners assume Marston Mat will be obsolete within months. Peacetime means you can take your time building proper concrete runways. The steel gets stockpiled at depots across the Pacific. Thousands of tons of it sitting in warehouses waiting to be scrapped or sold off. Then, June 25, 1950 happens. North Korea invades South Korea, and suddenly the US military is scrambling to establish air superiority in a theater where infrastructure barely exists. Those stockpiles of Marston Mat get pulled out of storage. Korea's terrain is completely different from Pacific Islands, mountainous with brutal winters and soil that freezes solid. Engineers wonder if mat designed for tropical jungles will work in sub-zero temperatures. They find out quickly. Steel gets brittle in extreme cold, but the interlocking design still holds. The flexibility that made the mat work on soft ground also makes it work on frozen ground. When soil freezes and expands, the mat flexes upward. When it thaws and contracts, the mat settles back down. No cracking, no separation. Kimpo Airfield near Seoul becomes the test case. September 1950, the airfield is in ruins. North Korean forces destroyed the concrete runways before retreating. US Air Force engineers lay Marston Mats right over the broken concrete, creating an operational runway in 72 hours. F-86 Sabres start flying combat missions from Kimpo while concrete repair crews are still jackhammering rubble on adjacent sections. The Korean War sees 38 airfields using Marston Mats, and the military starts calling it by a new designation, PSB, pierced steel planking. The name Marston Mats fades from official use, but the technology stays identical. Vietnam, 1965. The mat shows up again, now almost 25 years old. Some of it is literally the same steel planks used on Guadalcanal, still functional after 2 decades. Engineers lay it at places like Da Nang and Bien Hoa, creating dispersal pads for helicopters and expansion areas for existing runways. The Vietnamese climate, monsoons, extreme heat, acidic soil, is almost identical to the Pacific Islands where the mat was originally designed to work. It performs exactly as it did in 1942, but here's where the story takes an unexpected turn. After Vietnam, Marston Mats finds its way into civilian applications. Oil companies start using it in Alaska and Canada to create temporary roads and drilling pads across permafrost without destroying the fragile tundra. The same weight distribution principles that prevented bombers from sinking into Pacific mud prevent trucks from melting permafrost. Environmental groups actually support its use because it's removable. When drilling operations finish, you can pull up the mat and the tundra recovers, unlike permanent gravel roads. January 2010, Haiti. A magnitude 7.0 earthquake devastates Port-au-Prince. The international airport's runway is intact, but the surrounding infrastructure is destroyed, creating massive bottlenecks for relief flights. The US military airlifts pallets of Marston Mats, they're still making it, and lays it across damaged taxiways and parking aprons. Cargo planes loaded with medical supplies and food can now unload and taxi to parking areas that didn't exist 48 hours earlier. The technology designed to fight the Japanese Empire is now saving earthquake victims. Modern military forces still maintain stockpiles. The US Air Force calls it AM2 matting now, aluminum membrane version 2, because they've switched from steel to aluminum alloys to reduce weight. But the design is recognizable, same interlocking edges, same perforated surface, same basic concept Marston sketched in 1942. The British Royal Air Force uses it. NATO forces deployed it in Afghanistan to expand parking areas at Bagram Airfield. It shows up in disaster zones after typhoons, floods and hurricanes, anywhere you need instant infrastructure on damaged or unprepared ground. The original Marston Mats are still around too. You can find sections of them repurposed as walkways, bridge decking, even decorative fencing. Some Pacific islands still have operational sections laid during World War II, now weathered and worn, but still functional after 80 years. Wars get won by tanks and planes and ships. That's what makes it into the history books and the documentaries. But the reality is that wars get won by the infrastructure nobody sees. The unsexy logistics, the supply chains, the ability to turn a worthless piece of ground into a functional military asset faster than your enemy thinks is possible. Marston Mats changed the fundamental equation of how the Pacific War could be fought, and most people have never heard of it. Before these steel planks existed, capturing an island meant committing to months of construction before that island became useful. You'd seize the ground, then you'd wait while engineers surveyed, graded, poured concrete, and waited for it to cure. During all that time, your forces were vulnerable, and your newly captured island was essentially just expensive real estate. The Japanese understood this calculus perfectly. Their defensive strategy counted on each island taking so long to become operational that American momentum would stall. They'd dig in, make you pay in blood for every yard, and even after you won, you'd be stuck there for months making it functional. Island hopping was supposed to be slow. Marston Mats broke that assumption. Suddenly, you could land on an island and have operational aircraft flying from it within a week, sometimes within days. That changed everything about how aggressive the American advance could be. Islands that were previously strategic liabilities because they'd take too long to develop became viable targets. The Central Pacific Campaign, Aroa, Kwajalein, Saipan, worked because captured islands could immediately support the next assault instead of becoming expensive pauses in momentum. The numbers are stark. By the end of 1944, the US military had constructed over 300 airfields in the Pacific Theater. Roughly 220 of those used Marston Mats, either partially or completely. Without it, maybe a third of those airfields get built and they take 3 times as long. That means fewer forward bases, longer flight distances for bombers, reduced air coverage for naval operations. The entire timeline of the Pacific War potentially shifts by months, maybe a year. Look at the bombing campaign against Japan itself. The B-29 Superfortress raids that eventually forced Japanese surrender flew primarily from the Marianas, Saipan, Tinian, and Guam. These islands were captured in the summer of 1944. By November 1944, just 5 months later, they were launching massive bombing raids against Tokyo. That's only possible because engineers could lay Marston Mats run, ways capable of handling the heaviest bomber in the American arsenal in a matter of weeks. Traditional concrete construction would have meant those raids start in mid-1945 at the earliest, completely changing the endgame calculus of the war. There's a broader lesson here about innovation under pressure. Carnegie, Illinois didn't invent some exotic new material or revolutionary manufacturing process. They just looked at existing steel fabrication techniques and asked better questions. How do you make strength without rigidity? How do you make lightness without weakness? How do you make complexity simple enough that exhausted men under fire can assemble it correctly? The elegance is in the simplicity. Planks that hook together, holes that drain water, steel that flexes without breaking. Military historians often talk about the Pacific War as an aircraft carrier war, a submarine war, a war of logistics. All true, but underneath all of that is a war of engineering problems solved under impossible deadlines. Marston and his team at Carnegie, Illinois probably saved more lives and shortened the war more effectively than any single weapon system, not through destruction but through construction. They figured out how to turn mud into runways, jungles into air bases, and worthless islands into launching platforms. They made the impossible logistically feasible, and in war, logistics is everything. Those perforated steel planks with the simple interlocking edges didn't just build runways. They built momentum. They built a path to victory across an ocean, one steel plank at a time.